Hello, my name is Tim Lombardo, and I'm with EAS Consulting Group. I'm the Senior Director for Food Consulting Services. I would like to also introduce Majid Sharaf.
Hi, this is Majid Sharaf. I'm the Senior Director for Labeling, Cannabis, and Claim Services. Welcome, everyone.
Thank you. We are going to talk about food fraud today. Our agenda for the day is to go through a quick overview of what food fraud is. Continue that with a vulnerability assessment discussion, risk assessment, move into prevention strategies and mitigation strategies. And then at the end, we'll provide some resources for you to further understand food fraud. And we will certainly be able to honor any questions given how much time we have left towards the end. We also would like to thank Food Safety News for co-sponsoring this presentation. When we talk about food fraud, we are talking about adulteration of food. And there's actually 4 different types of programs that we should have in place to address adulteration. The first one being food fraud, which we'll talk about today, which involves the economically motivated, intentionally economically motivated adulteration. Our food defense program will address the intentional ideological motivated adulteration. And then our food safety and food quality systems programs should adequately address our unintentional adulterations of food or accidental adulteration. So these are the 4 programs that we should have in place in order to address all types of adulteration of our food. Food fraud constitutes several different types of fraud. The first one being mislabeling, which is the process of placing false claims on a package for economic gain. So for example, mislabeling a recycled cooking oil as a pure or virgin oil. Another type of food fraud includes dilution, which is the process of mixing a liquid of lower value with a higher value product. So often, olive oil is the biggest known product of concern for dilution, where lower grade of olive oils are mixed in with virgin or extra virgin olive oil. The next type of food fraud is concealment, and this is the process of hiding low quality of a food ingredient or product. And so this could be through, as the examples here show, poultry being injected with hormones to conceal diseases, or food colorings being applied to fruits to cover defects. Another type of food fraud involves counterfeiting, which is the process of copying a brand name or a packaging or a recipe for economic gain. These products or these foods are then generally not produced with the same level of safety assurances as the main brand is. Substitution involves the process of replacing an ingredient or part of a product of high value with another ingredient that has a lower value. So in the examples shown, sunflower oil being substituted with mineral oil. And then we have unapproved enhancements, which includes the process of adding unknown or undeclared materials to food in order to enhance their quality attributes. The most notorious is melamine, added to dairy products to enhance the protein value, but there is no nutritional benefit to melamine. The last component is gray market production or theft or diversion. And we typically would not consider this as a standalone part of food fraud, but it's typically incorporated into other areas. So when we were putting together our food fraud program, there's a few things we need to do. So one is to convene our team. And so this process is very similar to convening or to develop your food safety plan or your HACCP plan. And so we would convene a team specific to food fraud. We would create a food fraud prevention strategy plan, and then we would complete our vulnerability assessment. We would conduct a risk assessment and then develop some preventive strategies and mitigation strategies to address those vulnerabilities. There are several ways to conduct a food fraud vulnerability assessment. I like this one that I'll describe because it takes into account several different types of considerations that you would want to verify that you have adequate resources in place. So these considerations include history of fraud, economic and geopolitical considerations. It includes supply chain, your relationship with the supplier and your history with that supplier, and that supplier's history in production. Raw material quality control, storage and traceability, calibration, hygiene and cleaning, human resources, information given to consumers, and subcontracting. So you would look at all of these considerations and then apply a score, a vulnerability score, with 1 being a low vulnerability, 3 being a moderate or medium vulnerability, and 5 being a high vulnerability. Let's talk through each of these different considerations in a little bit more detail. So, history of fraud. Is there a history of fraud with a specific ingredient? Whether there are just reports of fraud or alerts from authorities. If there are none, then it's a low vulnerability. If there's a high number of reports or reports from authorities such as the FDA or USDA, then they would be a high vulnerability for that ingredient. Economic and geopolitical considerations could include having an ingredient or a product or components of those being either manufactured or transported through regions that have concern rising from their politics. So a perfect example of what's happening today is if you have ingredients or components or finished products being either manufactured or transported through, say, Russia or the Ukraine, then those components, those ingredients may have a higher vulnerability today than they had a year ago. If the political and geopolitical considerations are not of concern, then it's a low vulnerability. Supply chain. If all of the production, all of your ingredients come from a single company and that company supplies ethically, then they would have a low vulnerability. If you receive several ingredients, each manufactured from a different supplier across the world, then their supply chain may have a high vulnerability for that ingredient. Understanding the relationship with your supplier and that supplier history. So are you using a known and trusted supplier? Do they have a third-party certification? If that's the case, then they will have a low vulnerability. If it's a new supplier, either to you or a new supplier in the industry, then the vulnerability will be a little bit higher. So either a 3 or a 5. Raw material control, quality control. If the raw materials and packaging materials are verified prior to manufacturing. There are temperature controls and monitoring in place, weight controls and monitoring in place. Processing aids are compliant with US regulations. Then the vulnerability of that raw material is considered low. If the materials are not verified or the temperatures and weight checks are not conducted, processing aids do not have appropriate certifications, then the vulnerabilities will be higher. Storage and traceability. Is there storage that's established and indicated for each material? Does the supplier have a computer system that is available to assist with traceability and managing of inventory and the location within the supply chain? Are the ingredients individually identified and uniquely identified with lot numbers? If that's so, then you have a low vulnerability for this storage and traceability component. If not, then it is considered a higher vulnerability. Does the supplier have a calibration plan in place? Is it intense? Is it robust? Are their equipments calibrated and checked periodically and on a schedule? Does the calibration plan define what those tolerances are? And then are the corrections made? If so, then it's a low vulnerability. If the supplier does not have any type of calibration plan, then you may want to consider that a high vulnerability consideration. For hygiene and cleaning, does the supplier have a sanitation plan for not just the end of the production runs, but mid-run? Is there some other reason for a cleaning and sanitation plan? So for example, between allergen cleanings, are all detachable parts removed and cleaned before reuse? If so, then the supplier may have a low vulnerability. If there are no cleaning procedures in place or documented, then the vulnerability would be higher. Under human resources, do the operators have received training in GMPs, in traceability, in food fraud? Are these trainings delivered in a way that is for those who are responsible for the activities? And is refresher training conducted at least annually? If so, then that supplier would have a low vulnerability. And that ingredient would have a low vulnerability for that. If the workers receive no training or little training and refresher courses are not held, then the vulnerability would be higher. What information is given to consumers from that supplier in regard to your ingredient? Are regular checks made on correlation between the origin of raw materials and the processes carried out with the specifications that appear on the labels? If that information is provided, then it may be a low vulnerability. If there is no information provided, then the vulnerability may be higher at a 5. And then finally, subcontracting. Does the service provider use a subcontractor, and has that subcontractor comply with the same level of considerations as the supplier? Does that contractor have a good safety history, food safety history? Do they comply with third-party audits, preferably a GFSI audit? If so, then it's a low vulnerability. If the service provider, the contractor, does not have any type of approval system in place, and the subcontractor is not certified, then they would have a high vulnerability. So once we complete our vulnerability assessment and we score each of those considerations with a 1, 3, or a 5, again, 1 being a low vulnerability, 5 being the highest, we would look at each of those considerations and then apply a severity assessment, low, medium, or high, and then give it a 1, 3, or 5 score. For low severity, The adulterant corresponds to a negligible percentage of the total product, and the product complies with all standards that apply and does not have an impact on public opinion. So if these are true for, say, the history of fraud, then that supplier for that ingredient would have a low severity. For a medium severity, the adulterant may cause non-fatal harm or harm to long-term health by accumulation. The adulterant corresponds to a non-negligible percentage of total product. And the adulterated product does not comply with the standards in force, and the operator may be committing a serious breach. So if these are true, any of these are true, then it may be a severe, a medium severity. And then for a high severity, the fraudulent product contains an allergen or may cause illness with serious or potentially fatal consequences. The adulterant may lead to a public health concern. The adulterated product does not comply with standards in force regarding food safety, and the supplier or the operator may be committing a serious crime in producing that food. And the product has media pressure, and its adulteration generates major controversy among public opinion. And so that may be considered a high severity. So just as what we do with a risk assessment, hazard analysis and risk assessment for our food safety plans, we would do the same for our food fraud vulnerability and risk assessment. We would combine the scores from our vulnerability assessment and our severity assessment, and then get a score of high risk for that food ingredient. And high risk would be a score between 8 and 10. A medium risk of food fraud for that ingredient would be between 3 and 6. And then a low risk would be between 1 and 2. And then for each of those that we designate as a high risk, at a minimum, we would want to then develop some preventive measures, preventive strategies to address those. So for a supplier or an ingredient that has a history of food fraud, there are generally no preventive measures to apply. And so what our only recourse is to see if we can't change raw materials or the supplier. If that's not possible, then we would look into mitigation strategies, which we'll talk about in our next section. Economic and geopolitical considerations, same as with history of fraud, there are no real preventive measures in place for us to address. Our solutions are to change raw materials or suppliers if possible, and if not, then to implement some mitigation strategies around that. To address some food fraud in the supply chain, we would want to conduct audits of the supplier's supplier. To identify prevention strategies for the relationship with supplier and history, we could have the supplier complete a questionnaire, complete an audit of the supplier, require a GFSI or similar certification of that supplier to help to bolster the relationship of the supplier and its history. Raw material quality control, we would have sampling plans or temperature monitoring, checking of weights. All those would be in place to prevent food fraud from occurring. And storage and traceability, we would have electronic verification, identification, calibration. We would have validated calibration plans and procedures. Hygiene and cleaning, we have validated cleaning plans and procedures. Human resources, we would want to ensure that a training plan was in place that included traceability, good manufacturing practices, as well as fraud prevention. Information given to consumers, checking of flow charts, checking of weights, And then subcontracting. If a supplier is using a subcontractor to manufacture an ingredient, then a prevention measure, prevention strategy could be to audit that subcontractor. Now we'll move into mitigation strategies, and Majid will speak to this section. Majid?
Majid, it looks like your microphone is muted. Majid, I'll send you a prompt to unmute your microphone. Maybe that will help. Tim, do you want to just keep going?
I will
And then we
certainly
can come back to Majid. I'm not sure what's going on.
Yeah, I will certainly try. These were Majid's slides. So once we have in place our prevention strategies, and that's really the goal, is to prevent food fraud before coming into our facilities. We don't want the fraudulent food or ingredients to be in our facilities at all. So we have these preventive measures. But we can also then verify that the preventive measures are successful. And so these would be our mitigation strategies. And so some of the things that we have in place. So as the regulation states, and this is specific to dietary supplements, 21 CFR 111.320, you must verify that the laboratory examination and testing methodologies are appropriate for their intended use. And the degree to which the data is produced by a measurement process enables a user to make technically and administratively correct decisions for a stated purpose. Continue with the same definitions or similar definitions for fit of purpose. The laboratory shall use, oh, Majid, are you there?
I'm sorry, I'm here.
Okay, I'll let you continue then, thank you.
So what I was trying to, I was unmuted that the mouse was not working. I'm sorry about that. So let me go back to the beginning of my part. If I may, Tim.
Of course.
Give us a second. We just try to use the mouse again. Okay. It's not advancing or reversing. Okay, can you reverse them to the first one, please? So I'll see if I can. Okay, so the addressing food fraud also involves testing. So if we can move to the next one, please, Tim. So as Tim mentioned in 21 CFR 111.320A, it said that you must verify that the lab examination and testing methodologies are appropriate for intended use. And if we look next, if we look in the IUPAC dictionary of terminology, you can see that fit for purpose is defined as the degree to which data produced by a measurement process enables a user to make technically and administratively correct decision for a stated purpose. So this is the definition of a fit for purpose. Next. So if looking at ISO 17025, it said that the lab shall use test or calibration methods, including methods for sampling, which meet the needs of the customer and which are appropriate for the test and or calibration undertakes. Again, similar principle or the same principle or fit for purpose. Next. Next, Tim. So the ISO continues to say that even if the customer does not specify the method to be used, it is the lab's responsibility to select an appropriate method. Again, even if the customer does not specify a method to be used. Next. So fit for purpose is not only for a method of analysis, it also involves the equipment. So the equipment has to be calibrated, has to be properly functioning, and has to be maintained well. In addition to that, also the analyst has to be familiar with the process, familiar with the technology, so that he would be able to make decision when he sees the results in front of him or her. Moving to the next slide, please. So for a method, for a fit for purpose method to be acceptable, the method needs to be valid. And validation, looking at 21 CFR 111-320B, it reads that you must identify and use an appropriate scientifically valid method. So these regulations require that you use a scientifically valid method for each established specification. If we go next, looking at the ISO 17025 again, it defines validation as a confirmation by examination and provision of objective evidence that the particular requirement for a specific intended use are fulfilled. So this is how ISO 17025 is defining validation. Moving to the next slide. So validation is always a balance between cost, risk, and technical possibilities, which means that the lab should do its best within the constraints imposed upon the lab, considering customer needs, considering regulation and existing experience within the lab, equipment within the lab, available tools, and also the need for meteorological compatibility. So again, it becomes responsibility of the lab to work within these constraints. And if we go back to the previous slide, please. So as we know, validation should be conducted after a plan is documented, is written, and what you do is just you do the validation and record the result. You don't do the validation report right after the method is validated. So you have to have a document before you start in the validation process. Next, validation. So again, no, I think okay. Yes, we went back. So validation is required when you are using a non-standard method. So if you're not using a pharmacopoeial method or a method from a standard setting organization like AOC, for example, then it is required that you validate the method of analysis you'll be using. Next. In addition, also, if you are using a standard valid method outside of its own scope, then you need to validate what you're doing. Next. Then if you are within a lab and you're designing your own or you develop your own method, then once your method is developed, you need to do your own method validation. And as we know, method development and validation are not really completely different steps or separate steps. You do some method validation while you're doing a method development also. Next. In addition, validation also is required when you are modifying an existing valid method. So once you do a modification, you need to make sure that you validate your changes. Next. Also, validation is required when you're moving a method from one lab to another or when you're using a different equipment for the analysis. Next. Sampling is a critical part of analysis. So proper sampling is important, and it is an art. So taking an appropriate sample is a skill in itself, and it requires understanding of the technology and the chemistry of the project. Next. There are two types or two protocols for method validation. Single lab validation, where all of the performance characteristics we know that specificity or selectivity, linearity, accuracy, etc. All of these are, with the exception, as you can see, with the exception of reproducibility, all of these performance characteristics are performed within a single lab. Next. Collaborative study where multiple labs are involved, and this is tend to be to estimate repeatability and also precision reproducibility of a validation of a valid method. So this is where you do collaborative study. Next. Before I leave this section of the presentation, I want to share with you the difference between verification and validation. These are two different concepts. Verification is simpler procedure or simple process compared to validation. Verification is required when you are introducing a new lab. When you are introducing a new valid method into your lab. So you need to show that you are capable of having this method functioning within your lab as is expected to be functioning. Next. In addition, also, when you are moving the method of analysis, making a change, or you're moving it from one equipment to another, to a similar equipment, or you're moving you are updating software, or even when you are relocating the equipment. So in that case, you need to do a method verification. Make sure that the method continues to perform as it was performing before. Next. In addition, also, we do method verification when we observe that the method performance is changing over time. So you need to do method verification to make sure that the method is still performing as it was performing before. Next. So with all of these concepts, fit for purpose method does not have to be a complicated, elaborate method. As shown in this example, up to 1996, FDA was using taste organoleptic analysis to test different teas. So again, and so far, I mean, up to now, organoleptic or sensory analysis is still a respected method of analysis in a number of industries, such as perfumery and beverage industry. So sensory analysis is still being used and still being considered as a scientifically valid and acceptable method of analysis in some industries. Moving to the next slide, please. Taking an example of starch, it is according to the source you see at the bottom part of the slide, the finding the root cause for starch fraud. According to that source, cassava starch is used as an adulterant for more expensive starches. So again, we're looking at economically driven adulteration. So it is used as an adulterant for more expensive potato and corn starches. This is not only an economic driven adulteration, but also it constitutes an allergic hazard to consumers for those who are having cassava allergy. Moving to the next slide. So microscopical examination is considered a fit for purpose method to identify a starch granule. Looking at different starch granules under a microscope, you see that they have different shapes. The hilum has different shape, and the growth rings shape differently. So the structure of the starch granule under a microscope can be used as a mean to identify the type of starch we're dealing with. Next slide. And here I'd like to introduce to you another principle, another concept, which is orthogonal method. The orthogonal method is defined as an additional method that has a different specificity or selectivity to the first used method. And we move away, or we start to moving toward an additional analytical method when the first method is not enough to give us the answer we want. And this is where we introduce additional analysis. When you see possibility of adulteration, when we see related species that are similar, then you look into orthogonal methods. Moving to the next slide, please. I'm showing you an example of the benefit of adding additional orthogonal methods for analysis. So let's say that we're starting with the test using one method that has uncertainty of 40%. So this is exactly like as if you're tossing a coin. It's yes or no. Adding another test and moving to the next, please, Tim. So adding another orthogonal test also with an additional 40% of uncertainty. In this case, when these two tests are used together, the confidence level goes up to 84%. Next. Let's look at if we have a third orthogonal test and we are doing these three tests together, the confidence level goes up to 93.6%. So again, the benefit of having additional tests that look at the material differently, with different selectivity, will add to your confidence level and give you more information about the material you're testing. Next. Here we're having an example, looking at the three Echinacea species available in the supplement market in the US, Echinacea angustifolia, Echinacea purpurea, and these are the two most common Echinacea species in the US, and Echinacea pallida. On the left, as A, you see here Echinacea angustifolia, and below that, you see on the left also Echinacea as C, you see Echinacea purpurea. In the middle is Echinacea purpurea aerial parts, and on the right you see Echinacea pallida. So if I'm using macroscopical examination, if I'm using my eye to differentiate between Echinacea angustifolia A on the left and Echinacea purpurea C on the left, or Echinacea angustifolia and Echinacea purpurea on the left, and Echinacea angustifolia and Echinacea purpurea both on the left, and Echinacea purpurea aerial parts in the middle, visual examination is good enough to differentiate between these three articles. Echinacea angustifolia, top one on the left, A, has the outside surface looks, when it comes to color, it looks light brown to brown. The lower one, Echinacea purpurea, as you can see, it has a dark brown color to purplish brown color. So I can, using my eye again, I can differentiate between these two entire or two whole articles, botanical articles. And these are two related species. Similarly, I can use my eyes to differentiate between Echinacea purpurea, the one on the left, lower one, root and rhizome, and Echinacea purpurea aerial parts, simply because of the difference in shape. While if I'm looking at Echinacea angustifolia on the left, A, versus Echinacea pallida on the right, B, you can see that the color become really similar. So Echinacea pallida also has the outer surface, the color of the outer surface is light brown to pale brown. So macroscopical or visual examination of these different species at that moment becomes not possible, it becomes difficult and becomes unreliable. So moving to the next slide. Here we introduce another orthogonal method, which is HPLC. I'm using HPLC focusing on different chemistry of the three different species. So looking on the set of chromatograms on the right, you can see the arrows. The track number 4 from the left is for Echinacea angustifolia root. And you can see the arrow is pointing to a dark brown band and a yellowish, light yellowish band. These two bands are characteristic for Echinacea angustifolia root on an HPLC chromatogram. Compare that track Echinacea angustifolia tract 4 from the left to tract 5 from the right, from the left for Echinacea pallida, you can see that brownish band at around 0.3 RF is characteristic and it's not present in Echinacea pallida. Similarly, if you look at the chromatogram or the fingerprint for Echinacea purpurea, you still see difference between the fingerprint of Echinacea purpurea, which is track number 6 from the left, and Echinacea pallida and Echinacea angustifolia. So again, using an orthogonal method and focusing on one set of chemicals, alkylamides here, we are able to differentiate between 3 different species. The difference becomes even more visible if we move to the next. You see here, just applying heat to the plate. This plate was developed, sprayed with anisaldehyde reagent and examined under visible light, and we saw what we saw before. Now we applied some heat. You can see that the color changes, and also you see more, the distinction become even more visible. So again, using this HPLC test as an orthogonal method of analysis, in addition to microscopical examination, I can equivocally say that this is Echinacea angustifolia, this is pallida, and this is Echinacea purpurea. Of course, looking at the other set of chromatograms on the left, I'm looking at another set of chemicals, the phenolic constituents. And if we can move next, you see here the arrows are pointing to 3 different chemicals, 3 different phenolics. If you look at the track number 2 from the left, you see cynarin at the higher RF and echinocoside at the lower RF. Then you come to the track number 4 from the left, which is for Echinacea angustifolia root. You see that Echinacea angustifolia root has echinocoside, the most intense band with the lowest RF. It also has chlorogenic acid, which is the band in the middle, the light bluish band in the middle, and also it has cynarin, which is the band at about 0.6 RF, which is the top band, the second band from the top. So again, Echinacea angustifolia root contains echinocoside, contains chlorogenic acid, and contains cynarin also. Moving one track to the right, which is track number 5 from the left, which is for Echinacea pallida, it contains also echinocoside. But if you look up on the fingerprint, you see that cynarin is missing in Echinacea pallida. So Echinacea pallida root does not contain cynarin as a phenolic constituent. So again, using HPLC, this method of orthogonal HPLC, I'm able to differentiate between the 2 species that showed some difficulty when I was looking at them visually using my own eyes. Similarly, looking at the track number 6 from the left for Echinacea purpurea root, you also see a different fingerprint where echinocoside is absent in Echinacea purpurea root. Moving to the last track from the right, or the track number 7 from the left, is for Echinacea purpurea aerial parts, and where you see the characteristic bands for chlorophyll. Those red bands near the solvent fronts are always characteristic for chlorophyll in aerial parts. So seeing these bands tells me that this is an aerial part or an article that has some aerial parts in it. Moving to the next slide, please. Next. Okay, I described what this changed. Okay, then moving to a more complicated case. Tim mentioned about olive oil and how susceptible it is for adulteration. So looking at the case of extra virgin and virgin olive oil, and looking at the FCC monograph, it is defined as a fixed oil coming from the olive fruit, and it's only produced by mechanical press, with no heat, no refining, no solvent. So this is extra virgin and virgin olive oil. This is how it is known, or how it is defined in the FCC monograph. Moving to the next slide. Looking at the composition of virgin olive oil, once it's pressed from the fruit, it contains about 98% of triglyceride and some free fatty acids. The rest, the 2% part, is the unsaponifiable part of the constituents. And this contains, as you can see on the slide, it includes the phytosterol constituents, pigments, phenolic compounds, squalene, and tocopherols. So these minor components constitute about 2% of the constituents of virgin oil or of virgin olive oil freshly obtained from the fruit. Moving to the next slide. Olive oil has a high percentage of monounsaturated fats, monounsaturated fatty acids. And it's also characterized by the high percentage of oleic acids. If you can see, if you look at this chromatogram, you see most of the peaks, almost all of them, except a few, contains the O. O means oleic acid. So the fat triglyceride peak with an O means it has oleic acid. Some of them, if you look at the peak right before retention time of 8 minutes, you see it's all the triglyceride has only oleic acid, 3 molecules of oleic acid. So again, olive oil, virgin olive oil and extra virgin olive oil is rich in monounsaturated fatty acid, and most of these, and majority is oleic acid. Is also very characteristic. Olive oil is known to have very small amount of linolenic acid. So this chromatogram, what you see in front of me is characteristic for olive oil, extra virgin and virgin olive oil. But this chromatogram is good as long as you're dealing with the true material. Once you introduce adulterants, which tend to be, as you can see here, tend to be a fixed oil coming from different seeds like canola, corn, cottonseed, sunflower, grapeseed, etc. In addition, also refined olive oil, and where the olive oil is exposed to heat, and also some of the minor constituents are removed. So refined oil with such cheaper material is used as an adulterant in extra virgin and virgin olive oil. In addition to that, also the solvent extract pomace oil. What's left after the mechanical production of virgin olive oil is further extracted using solvent, and this what results in this additional form of olive oil that's later on refined and also comes into the food supply as a refined olive oil. In addition to that, also degraded virgin olive oil can be used as an adulterant on olive oil. Pigments, chlorophyll and beta carotene. These are native pigments present in olive fruit and in virgin olive oil and extra virgin olive oil, but they are used as an adulterant. For example, they are added to refined olive oil, so the color changes and start mimicking that of extra virgin and virgin olive oil. So these are the list of commonly known adulterants used to adulterate or extra virgin and virgin olive oil. Next, looking at the fatty acid profile of olive oil in comparison to other fixed oils, seed oils. You see olive oil in the column second from the left. You see that if you go down, that it mostly has 55 to 83% oleic acid. So oleic acid constitutes the majority of the fatty acids present in olive oil. Next. Next again, Tim, please. Okay, I wanted here to show you that linolenic acid content of olive oil. You can see that it's a trace amount. Linolenic acid, the presence of trace amount is a characteristic feature of olive oil. In comparison to other oils like canola oil and soybean oil, which these two oils contain a significant amount of linolenic acid. And this canola oil and soybean oil are two of the commonly used adulterants for olive oil. So seeing more of linolenic acid than trace amount indicate adulteration of olive oil with one of these oil or other oils. In addition to that, also if you look up, coconut oil has a significant amount of capric, lauric, and myristic oil. So seeing these oils, which are, as you can see again, look at the column on the second column from the left, olive oil, you see that olive oil does not have capric, does not have lauric, and has small amount, maybe very trace amount of myristic oil, fatty oil. So the presence of these fatty oils, fatty acids, I'm sorry, in olive oil indicate adulteration with coconut oil. So again, the use of fatty acid profile, which you get as a chromatogram, a GCFID chromatogram, the use of a fatty acid profile can be used as a way to identify and the quality, purity of olive oil, as long as it's not adulterated with one of the oil that is engineered or bred to increase the ratio of oleic acid in that oil. And we have an example here. So if we go to next, you see here, no, I'm sorry. Yeah, so if you look down, you see that C is sunflower. It's high oleic acid sunflower oil. So this is the type of sunflower that's engineered to increase the constituent or the content of oleic acid. So using that sunflower compared to olive oil can be, that's if we're adding an adulterant, this type of sunflower oil into olive oil, it becomes really difficult to identify this type of adulteration. So again, fatty acid profile is useful, but alone by itself is not enough to guard against adulteration. Moving to the next slide. Well, if we are focusing in fatty acid analysis on the ratio of oleic acid to palmitoylene, so we're only looking at the ratio of the two components, and we're applying chemometric analysis, you can see that group on the upper right corner is for extra virgin olive oil, EVOO, well separated from other different all kind of seed oil and other related fixed oil that can be used as adulterants in olive oil. So using this technique along with chemometric analysis, we are able to identify adulterants in the presence of extra virgin olive oil. Moving to the next slide. Here what we have here is the phytosterol profile of olive oil, second from the left, in comparison to other fixed oils. And if we move next, see that sterol, mostly the olive oil, the content of sterol in olive oil is mostly 75 to 90% of beta-cytosterol. The rest are minor constituents or traces. Next, looking at different seed oils, and if you move across, seed oils are known to be rich, or oils, fixed oil coming from seeds. That's what I meant by seed oils. So seed oil coming from, fixed oils coming from seeds are known to be rich in cambisterol, delta-7 stigmastenol, and stigmasterol. So if you look across, you can see that palm oil has 18 to 27% cambisterol, soybean oil has about 15 to 24%, sunflower 5 to 13%. The oleic acid-rich sunflower oil has also 5 to 13% cambisterol. Well, if you look at the cambisterol content of olive oil is less than 4%. So again, using the phytosterol profile as an additional orthogonal method of analysis will strengthen your ability to detect the adulteration with that sunflower oil which is a high oleic sunflower oil that was a difficulty, that was a problem when we were looking at the free fatty acid profile of the different oils. Moving to the next slide. Next. So looking at this slide, the absence of this class of components, stigmatidines, these are degradation products of different sterols. So the absence of these different components indicates the absence of refined oil, including refined olive oil. So when sterols are exposed to heat, the degradation happens and you end up with these dienes. And if we move next step. So this specific diene is the degradation product of beta-cytosterol. So the presence of this degradation product indicates the presence of a refined oil, and in this case, the presence of refined olive oil as an adulterant extra virgin and virgin olive oil. Next. It is known that if we focus on the minor constituent, on the 2% of the content of extra virgin and virgin olive oil or virgin olive oil, if we focus on these 2%, the profiles we obtain when we focus on this minor constituent will help us identify the purity and quality of olive oil in comparison to when we focus on the major constituents. In this example, I'm showing you the top image is for a jar that contains a virgin olive oil freshly pressed from a fruit, from the unripe fruit. So you see the green color of chlorophyll. So this indicates, this green color is an indication that this material is freshly virgin olive oil is freshly obtained. Once heat is applied, or by time, you see that the color changes to what you see in the lower part of the slide, where you see that yellowish color, or oil acquired this yellowish color. And this is because of you see also on the slide that the chlorophyll A and A prime degrades into phyophytin A and A prime, and these are the yellow colored material. In addition, if we can go to the next 10, please. So again, here you see the peaks for phyophytin A and A prime. Next, and here you see the additional peak for pyrophyophytin. And if you look at the chromatogram, lower chromatogram, you see more of the pyro compound coming as the material is heated. So again, these are degradation product of chlorophyll, and it's an indication that this virgin olive oil was either subjected to heat, like refined oil, or is an old aged oil. Next. So again, each individual test by itself gives you a piece of information, but it's not in itself enough to unequivocally tell you that this is true, an extra virgin olive oil or a virgin olive oil that's not adulterated or not misused or misstored. That's why if you're looking at the FCC monograph, you see all of this type of this long list of orthogonal tests that they are required to ensure the identity, purity, and quality of the extra virgin and virgin olive oil. So these are the tests you find in the FCC monograph for extra virgin and virgin olive oil. So I'll stop here. This is on this slide, Tim provided you with some additional resources, and next we'll be moving to the next, Tim.
So thank you very much. I know we're a little bit out of time now. We will address your questions individually. This presentation will be made available, or has already been made available to all attendees and registrants. So our contact information is listed on the back page of that presentation. If you have any other further questions, please please feel free to reach out to either of us. And we will send specifically to the questions that are on the that were requested. We'll send responses directly to those people. Appreciate your time today and hope everyone has a great rest of the afternoon.
Thanks, Tim.
Thank you.